Question 4, 4.1, it's about fossil fuels. The petrol fraction from the crude oil contains octane. Give an equation for the complete combustion of octane. So octane here in the question tells you is C8H18. Combustion is a reaction with oxygen. We'll balance that in a moment. Complete combustion of octane, so it makes carbon dioxide and water. Incomplete combustion would make carbon monoxide and water, or possibly even carbon and water if it was really incomplete. But it's complete combustion, so it's making CO2 and water. Now what I would always do is I would look to see if balance the carbon, say for example. So carbon appears here and it only appears in one of the two, so products, that is. So carbon appears in one of the two products, hydrogen only appears in one of the two products, but oxygen appears in both the products. So don't balance the oxygens first, do the carbons and the hydrogens that only appear in one product, and then do the oxygens last. So I've got 8 C's, so I've got 8 CO2s. I've got 18 hydrogens, so I must have 9 waters, 9 twos are 18, and now I can do the oxygens last of all, so I can add up these in here. 8 twos are 16, add 9 is 25, so I'm going to need 12 and a half. 12 and a half times 2 is 25. The combustion of petrol in car engines producing a pollutant nitrogen monoxide. Give an equation for the reaction that removes nitrogen monoxide in a catalytic converter. So what a catalytic converter is, it removes two very poisonous gases, nitrogen monoxide and carbon monoxide. So if I get any of the petrol that is incompletely combusted, so incomplete combustion in a car engine, that's likely to happen, remember, because you haven't got a plentiful supply of oxygen coming into a car engine. There's a limited supply, so I'm going to make some carbon monoxide due to the limited supply of oxygen coming into a car engine. So I've got to get rid of those two gases that are poisonous, the nitrogen monoxide and the carbon monoxide, and they come together to make nitrogen, which is a gas that's abundant in the air, so about 79% of the air is nitrogen anyway, so that's fine, and some carbon dioxide, which isn't great because it's a greenhouse gas, and we know that carbon emissions from car engines make carbon dioxide. Hopefully the carbon monoxide will be removed by the catalytic converter. So I've got nitrogen monoxide NO, CO makes N2 and CO2. I've got to then balance it. I've got two N's, so two NOs. Again, balance the N's and the C's first. Leave the O's until the end, because there's more O's. The O's appear in both of these reactants. So do the N's first. N2, two N's, two NO. I've got CO2, so I'm going to need 2 CO2s to balance up the oxygens to make 4 oxygens, 2 CO2s. Sulfur dioxide is produced in the combustion of fossil fuels because there's some sulfur content in things like coal and oil. The total emissions of the sulfur dioxide in the UK have been fallen dramatically. Okay, sulfur dioxide is now removed from the flue gases. A flue means a chimney, so the chimney gases in power stations by reaction with calcium oxide. So calcium oxide absorbs any sulfur dioxide that might be released and cause acid rain. In 1970, the total UK emissions of sulfur dioxide was 63.49 million tonnes. So the only problem with this question is that you're dealing with big numbers, and it tells you here that 1 tonne is 1,000 kilograms. So 6.49 million tonnes. I've got 6.49 million multiplied by 1,000, and it's in kilograms as well. So I'm dealing with very, very big numbers. Apart from that, the calculation is not too bad. Calculate the mass in kilograms of calcium oxide that would need to react with this mass of sulfur dioxide. Give your answer in standard form. So let's start to work out the number of moles of sulfur dioxide. So first of all, SO2 emissions 6.49 million tonnes. Let's sort out these million tonnes. So a million is 10 to the power 6, so I've multiplied by 6.49 times 10 to the power 6. I've worked out the number of tonnes. I've got rid of the million. 6490000. Or you could put 6.49 times 10 to the power 6 if you prefer it in standard form. And now I'm going to get rid of the tonnes. So the tonnes, a tonne is 1,000 kilograms, so I'm going to multiply by 1,000. So I've got 6,490,000,000 kilograms. Now I'm going to get into grams, so I'm going to multiply by 1,000 again. So I've got 6,490,000,000,000 grams. Again, you can put it into standard form if you wish. So you could have 6.49 times 10 10 to the power 12 if you wanted, and so now I've got it in grams. So now I can work out the number of moles. Remember, it's got to be in grams for moles, because moles is mass in grams divided by mR. I've got the mR of the SO2 as 64, because I've got a 32 for the sulfur and 2 16s is another 32. So 64, 6490000000000 divided by 64 is this large number here. From the equation, the moles of calcium oxide has got to be the same, because it's 1 to 1. 1 in front of the calcium oxide, 1 in front of the SO2, so the number of moles of calcium oxide is the same. Then you convert it back again, so moles is mass divided by mR. This is the mass in grams, so this is the moles. Mass in grams I've got to work out. mR of calcium oxide is 56, because the calciums are 40 and the oxygens are 16. 56. Multiply this number by 56, and I've now got the mass in grams of calcium oxide. It asks for the mass in kilograms, so if I divide by 1,000, then I come out with 5,678,750,000 kilograms, or I could put it in standard form, something like 5.678 multiplied by 10 to the power of 9.